Ah, me. Yes, draft science video. So I'm going to deal a little bit about the Feynman irony, we'll call it. The Feynman irony. So there's two video series, one he did in the 60s, I guess, and one he did in the 70s or something like that. But anyway, Auckland versus, I don't know, Pennsylvania or something, I don't know. This might be New Jersey, I don't even know where he was. Anyway, this is probably California. Yeah, California. Yeah. Anyway, so there's this older one. So the older one is where he critiques the idea of the particle gravity theory. And then the other one, he starts talking about a checkerboard and the idea that physics could reduce to this checkerboard. And so they're sort of interesting contrasts because he kind of, I think he wanted that idea to work. This idea that it gets really, really simple and that he actually says words like, and the problem is just a problem of numbers. There's just so much of it that we can't make a picture of it. It's too dense, it's too thick, there's so much going on that we can't really grasp it. We're not coming up with any way, he didn't say these words, but yeah, we're not modeling it. Like where I think they could model some of this stuff. If I had a computer that had the, I can do some stuff with the browser now. It actually has some things where you can do this bouncing ball kind of idea. But, it's going to take some time to turn that into 1,000 bouncing balls. And, yeah, I just can't apply the time right now. But I think if I can put the arrow field in movement under controlled circumstances, that you can make some of this stuff visual, where you can actually model it and see it. And if you see it, then you can understand it. So anyway, but these are two things. So he's kind of backed into being some kind of authority on particle gravity when he didn't really study it that hard. And but he's sort of cited as, well, look, Feynman thought it couldn't work, so therefore it couldn't work. He's another person saying, he said those exact words in this video. The problem is it doesn't work as a model. But, my argument was because he wasn't doing the checkerboard thing, because he really didn't take it to its native world. Instead, he was leaving it in this world, and he made the analogy to raindrops. Right in this video. I don't know if this is the exact spot, but he just compared it to raindrops.
There's a law in physics called Faraday's law, which says that in an electrolysis.
Well, now he's on Faraday, but it was right in here somewhere. Anyway, it's not going to go back. I shouldn't have tried, because now it's going to be doing this little wheelie spinny thing. And you see, you have
very little mathematics is needed in the fundamental.
There's very little in the fundamental. See, that's the whole idea, is you're trying to get to this rudimentary function. And so anyway, I'm just trying to point out that there's sort of irony that Feynman had some respect for this idea of a fundament, something really simple, and but accidentally was part of the crowd, part of the instrumentality that made thinking that way a crime. Like you're being a cliche idiot if you could fall for this, mechanical gravity, because it's just too easy to dismiss in by comparing it to raindrops. So anyway, I thought of a better comparison would be like if there was a row of machine guns on the side of a really long road. So it doesn't matter. It's a really long road, and there's machine guns evenly spaced, and they're shooting bullets. You drive your car. Now, it really doesn't matter if you park your car or you drive as fast as you can, 100 miles an hour. You'll hit just as many bullets. So it just doesn't matter. You could just leave the car parked, and it'll get hit with a certain number of bullets, and that's how many bullets it's going to get hit by. And it'll be the same exact number if you drive 100 miles an hour down that road. Because for every bullet you hit by moving, you'll miss one by moving, if the bullets are coming from the side. See? And that's sort of one of these facts where you just say, oh, so if you change this rain scenario into a subtly different scenario, you can sort of get the idea that maybe this won't make a difference as you're moving through a field. Alright, so here's the problem. The problem is that as gravity, when there's more arrows going this way than this way, and you're in the middle, you'll end up moving this way. Okay, so I mean, well, you know, the way there's more arrows. The more arrows coming this way, then you'll absorb some of them, and you'll end up acquiring movement in the direction of the imbalance in the force. That's what matter does when you put it in an imbalanced force. It will move. That's why airplanes go up, all kinds of things. Well, it's technically not why airplanes go up. Bad example. But anyway, it's why helium balloons go up or something. I don't know. I'll have to come up with some. The physics is a little different than chemistry, so you can't get fooled by chemical examples. But anyway, you get the idea. The stream's streaming, you're going to go with the stream. Now, when the stream's balanced, it's a pond, well, then you can just sit, because there's just as much coming from this direction as that direction as any direction, so you just kind of sit there on the water because the water isn't moving. Now, if I'm in the pond and I move through the pond, the idea is that, well, I'm going to be moving into more pond over here. So that's technically, you know, by some kind of Einstein logic where all velocity is the same or all movement is the same, I would technically be imbalancing the force. There would be more pressure here and less pressure here, and so now I should be going, it should stop me from moving. It should be an impediment to my free movement. And clearly, that's not happening light doesn't slow down. Lots of things move through the field, and it doesn't slow them down at all. And that's where you get back to this kinetic thing. And now the picture I didn't draw, which I might have to add to this, maybe I'll add a paragraph on this, just because, you know, that's why I'm doing this video. Essentially, is just because I'm trying to think of some way to explain it, you know, simply. But anyway, the interaction not shown here is the head-on interaction. Okay, and obviously the complete miss interaction. So I mean, the two, obviously you can't even draw where they're going separate directions. Obviously that event doesn't happen, but the head-on event does happen. But it's like they go right through each other. Okay, it's technically, you know, you can sort of understand kinetically. It doesn't matter how you imagine it goes, that they bounce completely off of each other or they go right through each other. You know, the end result is exactly the same. There's going to be an arrow here and there'll be an arrow here. So if two arrows go into each other at this point, you know in the next moment of time there's going to be an arrow here and an arrow here, and it really doesn't matter whether they went through each other or they banged off each other. It's the same universe in the end. And so you kind of have to understand that if matter's moving through the field, then all the arrows going in the direction of the movement, or in the opposite direction quite obviously, those are all kind of neutral. Nothing's really going to change. And the only arrows in balance here, the only arrows that are part of this game we're talking about, are the arrows going tangential to the force. So I would say that the same is true for gravity. When there's an imbalance in the force, the arrows getting changed are the ones going up and down, the ones with a tangential element in them, some angle of impurity from the pure direction. And those are the only ones that are getting changed. So, you know, getting converted from one to the other in terms of what the matter possesses. And now will contain, and now it will have its own imbalance, causing its own acceleration, and ultimately acceleration is velocity. Acceleration is just acquiring velocity. So yeah, so then it'll be moving through the field. So I was trying to think of some way to illustrate. So this box is, let's say this box has just as many arrows going up as down, as forward as back. So it in essence is an orbit, it just doesn't look like one. And I want to move that box. Well, you can sort of understand that the arrows already going the direction of the movement, they're going the speed of light in this theory. So you could almost see that if I mark them in green or some color, all the arrows are tending to go this way, which there's one there, there's one there. Doesn't seem to be too many up here. My randomness wasn't too random. But anyway, you can sort of understand that they're moving the speed of light. So in the next moment of time, let's just call it a moment, they would all be out here. But all the other arrows, the ones going this way and this way and this way, they didn't do that. You know, they're not out here. So they don't just move along with these other arrows. The real point is that the ones pointing in this direction somehow have to be slowed down a lot. I mean, you know, in the sense that they have to be almost invisible for more than half the time, and these ones have to be, you know, converted into those and moving this way. So in a way, you can think, you know, so there's lots of ways of thinking about it. And I was, you know, thinking of different angles to how you would think about it, but you could think about it like, yeah, okay, this piece of matter isn't moving the speed of light, therefore all these forward arrows have to not be moving. I mean, they can go from here to here, and then they have to stop and wait for everybody else to catch up. So you can kind of think of this arrow goes over to here, stops, and then it says, okay, you here going down, you can pretend to be me for a while. So yeah, I'll give you my identity, and now you go over here, and then you can become a down arrow again. So I'll give you my clothes, you wear my clothes for a minute, you drive over to here, okay, and then you put your old suit back on, and you give the suit to somebody else who's going the wrong way, and he comes over, and then he gives the suit to somebody else, and he comes over, and so you're just basically waiting for everybody to get here before you start going forward again. And so you can sort of get the idea of what's involved when matter is moving. And it's very different than the force being imbalanced. When matter is moving, the matter is doing a lot of identity changing. It can't, you know, it's not just some sort of, yes, this is the matter and it moves. No, it's all of the matter has to do this identity change in a sense. It all has to be like a laser beam for a while. So that's another way to look at it. That the matter, think of it as that it can only do one direction at a time or something. And so what it's really, so you know that this direction and this direction are kind of irrelevant because they balance out in the end. And so the only thing really relevant is this direction and this direction. So you know if it's moving, it's not going to be doing as much in this direction. So let's just ignore that and let's just pay attention to this direction and how much of the time is it spending going in this direction, kind of like as a laser beam. So it's like all the matter for 1/10 of a moment doesn't do anything else that it was doing, and it all goes the speed of light in the one direction, like a laser beam. Well, when it's a laser beam, it can move through space without being affected at all. Remember the straight lines crashing into each other. So when it's going the same direction as the stuff it's banging into more, it's the same thing. It's a neutral. It doesn't mean anything. So when it's moving in the direction of its velocity, when it's moving in the direction of its velocity, yeah, like it could avoid doing that. But kind of, you know, the only thing that's really impacting it is the arrows coming the opposite way. Those are the ones supposed to be doing all the damage. But in a sense, those can't do any damage because they're going the same way. So having more interactions with arrows going the same opposite way of your velocity is totally irrelevant to your progress. You need to bang into the ones going some other direction for those to have an impact on you. For the impact to be noticeable, to have a consequence somehow to your matter. So anyway, so it's just basically thinking of it in terms of the net product of this thing is a certain leftover. So if it has a velocity, it means it just has a few extra arrows going this way. So in a sense, you can just wipe out the whole matter and just have the 3 extra arrows and out here as a representation of where this is moving. And those are the only arrows that are really doing anything, because the rest of it's all canceled out. So these are the only relevant arrows, and as 3 arrows going in one direction, you can't slow them down with anything coming the opposite way. You can sort of, like I said, kinetically understand that that's the neutral. The head-on collision is the neutral. So even though it's, you know, I said this months ago, but even though it seems like the head-on collision would be the more significant event, you know, to our perception, we think of 2 cars crashing into each other head-on as being the more significant event. You have to sort of understand that these cars are always crashing at the speed of light. They can't crash any faster. So head-on collision doesn't really mean anything, you know, in a sense. It's like the parked car and the machine guns. It just doesn't mean anything. You can't run away from it. So it's just, you're going to get hit with as many bullets if you sit still as if you try to go 100 miles an hour. It's the same thing. Alright, another way I thought of it was adding the time dilation component. And you can just sort of think about it in that sense, in a way that, okay, the arrows not going forward are just sitting here. So the matter's moving, and they don't move. They can't move. They can't move with the matter. They have to be converted into an arrow to get someplace. So the matter's leaving them behind, in a sense. And you can just sort of understand that, in a way, you can just think of them as just being non-existent during that time, and the only existent time will be the time, when you convert them into an arrow to move them there. Technically, right? Because they have no velocity in this direction. The only thing that has velocity in that direction is this. So even though the matter has direction and a velocity in a direction, only a certain number of arrows have that velocity in a direction. The rest of the matter has no idea, technically, it's moving. It doesn't think it's crashing into more stuff or doing any of that stuff, because it's not. It's just plainly not, because it doesn't move with this. Because this arrow is going here, this arrow doesn't go with it. Just as if this arrow was going down, this arrow wouldn't be, going down. It would be doing what it's doing. It's be going across. It has no obligation to recognize what the other bits are doing. So that's sort of the way to understand it, is most of the matter isn't moving technically in the direction of the velocity. Most of the matter is doing the orbiting thing and pays no mind, in a sense. It's just not relevant that the thing is moving, because it's not. It's just staying where it was. And the only way it moves is you have to make it disappear for a while. You have to make it just go away, blip it out of existence, essentially, and have it arrive over here. Just arrive, because technically it wore some other arrow's identity for a while. It didn't exist. It became an arrow doing the laser beam thing, going the speed of light in this direction it was going before, which can't go any faster, so technically it's can't get anywhere faster, because it's already going as fast as it's going. It's an arrow. So I guess the argument I used with the changing clothes is about the same argument as I'm saying here, but I'm just kind of arguing that you just blip it out of existence for for the amount of time it would have taken to move it here. So you just pretend it doesn't exist, and you move it here, and you move it here. You move them all up to the right location, and then you start the game again, so to speak. So, I mean, it's one way to understand it, but you can sort of understand that. I convert all... So velocity is basically just converting more arrows into this direction, right? So you can just imagine if I took all these arrows and made them all arrows going the same direction, that would effectively be a laser beam. So I would effectively take something that's matter, right? This all adds up to orbits now. There's this many going down, it's going up, it's going across, it's going this way. Well, obviously it has the other dimension in it. So there's this many going this way as there are going that way. And when I convert, when I give this thing velocity, what I'm essentially doing is just converting all the arrows into arrows going that way. And there's no more orbit in there. There's no more pattern. There's no more anything, because every arrow is just pointed that way and going that way, and that's a laser beam. So essentially what I'm saying is, when the matter is semi-stationary, even though it doesn't have to have relatively stationary to the force it's feeling. So when gravity is hitting this, the matter still has all its tangential components. It still has a bunch of bits going sideways to the gravity, and those are the bits the gravity now can still hit, because the gravity is banging into them at the normal rate. And so the imbalance, having an imbalance in the field, more arrows coming down than arrows coming up, will affect stationary matter, because the matter has all its tangential elements intact. They're not missing the force imbalance. They're feeling the force imbalance. Where if I move the matter, the force imbalance on this thing is never felt, because this thing, never move sideways. The down arrow cannot move sideways. So I'm just trying to make the example that where this gets illusionary or confusing or kind of fuzzy is just that there is a distinct difference between a force imbalance on stationary matter and a force imbalance created by matter in motion, and that difference is completely wiped out by the amount of the imbalance. So like I said, we're back to the argument. If I have 3 extra arrows worth of velocity in this direction, so let's just say I had we're just doing it in 2 dimensions. So there was 20 arrows going down, 20 arrows going up, 20 arrows going back, 20 arrows going forward. Now this thing would have forward velocity if I had 21 arrows going forward, or 22. And then you would have 19 of all the others, or 18, whatever, to balance that out. So I have these 3 extra arrows here, 3 extra little arrows is the net product of this thing. You can just see that those 3 arrows would have no problem with the velocity of the field coming this way. It just wouldn't make any difference to those 3 arrows. You can't get rid of them that way, because you still have to hit the tangential arrows. And the tangential arrows don't hit more field because they're not moving. They can't be crashing into more, they can't feel this greater pressure because they don't move sideways. They don't move this way, they just go that way. So anyway, so you can see my dilemma. It's a subtle fact, and so yeah, there's lots of little ways to try to explain it. Like I said, like it doesn't exist and it moves, or it changes its shape and moves. I mean, it changes into something else and moves, or how exactly to explain this, that there's some portion of time, and that's all this is really about, is time, over a period of time, of what condition this matter's in. And it's essentially saying that when it's moving, it's all moving at once. You could almost just say a second is only 1/10 of a second long, and it just moves like a laser beam all at once in that one direction, and then you could just forget about all the other movements. But I mean, that sounds like you're leaving something out, but you're really not, in a sense, because in a sense that's what's really happening. And as you can understand, that the laser beam would be moving 1/10 of its normal speed, because it had to wipe out 90% of time, where things weren't what they used to be, where you're dragging these down arrows to the start line, where you're making them move. You can only make them move by converting them into a forward arrow. That's the only way they can go that way, is they have to become this. It still isn't quite as good as I need it to be. But I guess what I'm just saying is there's a difference between imbalances created by the movement of a field and imbalances actually in the field. So those two things are different, because you have to understand what this has done to the equation. What this mixture has meant, that there's already a bunch of forward arrows. When this is standing still, there's a bunch of forward arrows that quite obviously have to have their identity changed. If the stuff inside of me that's going that way was allowed, was allowed to go that way, it would go that way the speed of light. It would leave my matter and go, just be gone. So obviously something's happening to it where it's stopped and it becomes something else for a while, or it does something else for a while, because it's not going the speed of light. It doesn't leave my matter. It stays here. And the only way it can stay here is it has to be switching identity with other bits. I mean, it sounds good enough, but like I said, I don't know how to write that. I wish somebody else was doing the writing. Yeah, I wish I had people. Einstein had people to do his math and stuff. I need people. Anyway. Yeah, I don't want to beat this one to death. It's just this is the only subject I was, I wasn't satisfied with my last explanation. I'm not terribly satisfied with this one, but I think I'm getting to I think all I need to do is give you some hope of saying, yes, I sort of understand how, the bits inside of me going into, like if I have a velocity of 10 miles an hour, 10 miles an hour is a lot slower than the speed of light. So obviously the bits inside of me that are going forward at 10 miles an hour, I mean at the speed of light, are going a lot slower somehow. Somehow they're not going the speed of light, they're going 10 miles an hour. So they can't be doing that forward thing. They must be doing some other direction. And they're not really doing another direction. They're still going forward. It's just that they're doing the same direction for the parts that didn't move. So the parts that didn't move are using their forwardness. They've lent their car to the other bit. Maybe that's a way of saying it. See, this one has a car and it drives its car to this edge at the speed of light. And it basically says, okay, now you can borrow my car, down guy. And so the down guy borrows the car and he drives to the edge. And the next guy says, okay, I'm here. And, and then he lets somebody else borrow the car. But they all have to borrow the car to get over here. And that's what makes it hard for them to go the speed of light, is because they have to spend this matter can't go the speed of light because it has to keep lending the car to somebody else. So, it can only go the speed of light while it's driving the car, and then it has to stop and give the car to all these other assholes and say, okay, I'm over here, how the car gets to them, I don't even get into that, but you know what I mean. Point is that, the point is there's a difference between a force imbalance in the exterior world and the force imbalances that happen inside of here, and that the two technically do just wipe each other out. So there's no, you can't, once you're in imbalance, you're always imbalanced in the direction you're moving, and so your imbalance is exactly consistent with any imbalance in terms of what you're banging into. And so you can never really get rid of your imbalance because it's exactly compensated for by your movement. Your movement is exactly compensating for the extra pressure, so you just keep doing it because you've already compensated for the extra pressure. I think that's enough. Try again. I'll work on it some more, but not today. I mean, I hate to get just stuck in this one subject forever, but it's sort of, it's not really that, to me, frankly, it's not that important, just because I would say, well, okay, if I do the rest, if people think about the rest of this stuff, they'll understand, oh, well, there's probably a reason for that. I really shouldn't have to, they'll probably figure out that, oh, yeah, the rest of this makes enough sense that I can cut that some slack, because, yeah, I sort of get it, that there's some math in working there. There's the machine gun. Maybe I'll just use the machine gun argument. It's just that, we have this perception that that somehow would help if you're moving, but it's not going to change anything. Same bullets in the end. Alright, that's enough. Same tangential bullets. Same number of bullets hitting bullets going, tangent bullets. Can't change the tangents. Can't change the number of tangential interactions. I guess that's the way I should have said. See, the faster this thing goes, the fewer arrows that are actually going this way and this way and this way and this way. And so you really can't change the number of tangential interactions, because if I make all this go the speed of light in this direction, it has no tangential arrows. So there's absolutely no capacity to hit one, right? You can sort of get that, right? So, maybe that's a better way to say it. So that as you gain velocity, you reduce the number of arrows going tangentially to your velocity, and thereby create an imbalance in the direction of your velocity. You've already created the imbalance in the sense that now there's less arrows to hit, and less arrows to hit, having more bullets coming at you, but now you have less things for the bullets to hit. You know what I mean? So as your bullets increase, the number of things you can hit decreases. You get it? So the number of bullets that don't hit anything stays the same. Right? Right? Okay. I think maybe that's the way to say it. So, so let me see if I got that one right. Yeah, okay. So as I gain velocity, I start losing arrows going tangentially, proportional to how many extra arrows I'm going to be hitting from this direction. This is the only direction I'm really hitting extra arrows, right? Because the side ones don't matter. So the only extra ones I'm getting are from this direction. Technically, you know, it's this direction, but it's always a percentage of component from those directions. And so you just, for every component you go, for every bit you move up this way, you end up being more tangential than this, and so you end up being a tangent, which is irrelevant. You know what I'm saying? The tangential point always destroys your forward element, so they're essentially the same as a tangent. Anyway, I mean, you'll miss them this way just as much as you'll gain one from this direction, you'll miss one from this direction. So as soon as you put it on a tangent, your likelihood of missing is the same as an up or down. So that as soon as you bend it off the middle, you've already turned it into a tangent, essentially. But anyway, how do I get lost in that? So yeah, so the theory is that as you gain more velocity in a direction, you lose tangential arrows. Less arrows are going this way and 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 this way. So you're obviously hitting less, even though there's more arrows going this way. There's fewer targets, so more arrows miss. More of these arrows won't hit anything. So you know, it's the same amount that won't hit, but I'm just saying because there's fewer targets. And as you eliminate the targets and you increase the number of arrows you're shooting, you're still only going to hit the same number of targets, and you're still going to miss by the same percentages. Let's just put it that way. The percentage of hits to misses will never change because you keep making the target smaller as I give you more arrows to shoot. So I give you more arrows to shoot, but I made the target smaller, and you can figure out the math that you're going to hit the target. You're not going to hit the target more times because the target got smaller. Okay, maybe that's the way to say it. Alright, I sort of like that. Maybe I'll work on that one. Come on. I think you got that one. Alright, I have to start. Oh, I gotta do stuff. I gotta painting sitting there waiting for me. Must paint, must do other things with my brain. I get lost in these problems. But then, you know, this is sort of what's irritating me about a lot of these conversations where people diminish the amount of effort it takes, and you know, just like some asshole, I just sat here and just made up some Sasquatch theory, you know, in 15 minutes and blah blah blah. Yeah, and it's really possible. It really is possible to make up crap. I mean, I made up that thing for half of the day where I could invent something that makes it possible to bend one of my arrows by just saying my little arrows have little fins. You know, and if they have a fin on the right, then they get bent by the gravity in, and if they have a fin on the left, then they don't. And, you know, you can just invent little silly shit like that. You can tell fables and make them sort of relevant. You know, you can give things magic powers or fake powers, but it's a lot more difficult when you're really trying, you know, stay in the box of, you know, not using magic powers. And it's work. You know, I'm a little pissed off at some of these people. I just resent it. I just resent this attitude that, you know, you spend 3 years and thinking and really thinking, you know, and thinking is irritating. I mean, I kind of compare it to when I did have a stroke, and you know, you learn how to use my hand again, and it was the most irritating kind of physical activity. You know, just doing this was incredibly nauseating and tedious, just to, you know, relearn to use your fingers. And yeah, that's kind of how, you know, when you're thinking about an abstract problem, you're trying to get all of this crap in your head, and you're trying to organize your brain enough so you can actually conceptually understand what you're trying to model. It's really not fun. And painting has that some too. You know, some painting goes really easy. You know, it says, okay, the shape, well, it's not a square, it's not round, it's something like this. You know, but when you really get into it, and you're trying to balance all the contrast in the entire painting, and what sticks out and where your eye goes and all that kind of, it gets a little bit gnarly and uncomfortable. Well, anyway, I'm just sick of people who haven't done this shit, wagging their fingers at the others saying, you're just stupid or you're just silly. Fuck you, you're just useless. Anyway, till next time.